Hello, today I want to show you how to measure a capacitor with an Arduino and two resistors. First of all, the theory of a measurement. If you put a voltage over a capacitor, it starts charging, depending on the resistor you use for. And this is the charging curve of the resistor. After 1 tau, it's 63% charged. And after 5 tau, it's getting higher and higher. It's 99% charged, so it's almost full. But we use the first step here, the 63% for 1 tau. So this is the charging curve. And if we are charging the capacitor, the time constant tau is R multiplied by C. This means resistor multiplied by capacitance. And after 1 tau, as I showed you, it's 63%. An AD converter, an analog to digital converter of an Arduino with 10 bits has 1024 steps. That means from 1 and up to 1023. And 63% of 1023 is 647. So if the analog converter reads this value of 647, then we are sure that the capacitor is charged to 63%. So that's the charging. And now let's have a look at the discharging. An Arduino pin can deliver up to 40 milliamps. So we have to choose the right discharge resistor. We want a fast discharge time to start the next measurement. So with the Ohm's law, we get 5 volts divided by 40 milliamps, means it's 125 ohms. And I've chosen for my circuit 220 ohms resistor. So, and this is the circuit we use. We have a charge voltage going over 10,000 ohms or 10 kilo ohms. The current is charging the unknown capacitor here. The AD input measures the voltage at this point, and after it reaches that limit, then he is ready. I can calculate the time and the capacitance, and then we have to discharge it with another pin over 220 ohms resistor. So all we need is 2 resistors and the unknown capacitor. So this is the circuit on the breadboard. You can see here the Arduino Nano. Here are 2 capacitors which are unknown and which has to be measured. And we have on this breadboard a plus line going over all the way here. Minus line is that blue one, and the plus line the red one. So we can connect the capacitors between plus and minus. This makes sense because electrolytic capacitors, you have to take care of the polarity. So, and here's the Arduino with 2 resistors. You can see here A4 pin is connected over 10 kilo ohms resistor to the plus of the capacitance. And the measurement pin is A6 with a wire bridge also to the plus of the capacitor. And the discharge resistor is here, 220 ohms, connected to the A5 pin and the plus of the connector. And the minus is connected to the ground of the Arduino Uno. This wire is not necessary, it's from an earlier circuit, it's for measuring the VCC. You can see this video here too. All we need is the 2 resistors and 2 wire bridges and an Arduino Nano to measure the capacitance. So, and of course the Arduino program. Let's have a look at the program. So it figures out that we can measure a capacitance between 10 nanofarads up to 2000 microfarads with an error of about 1 or 2%. Below 10 nanofarads, it's getting higher than 10 or 12%. So this is the limit. So first we define the pins and the resistor. The charge pin is A4, as I've shown you on the board. Discharge pin is A5. These are connected with 10 kilo ohms and 220 ohms resistors. Measurement pin is A6, AD input of course, and the resistor is 10 kilo ohms. I measured mine to get a little bit more accurate result, and mine is a little bit less than 10 kilo ohms. I inserted here the right figure which I measured. So in some variables, the start time and pass time until we reach the 63%, and microfarad and nanofarad, which we need later for the calculation. So now we start with a program. First we make the setup section with a charge pin as an output and digital write to low, so it has no 0 volts. We start the serial output with 38,400 baud and print this line. And then we come to the loop section, which is repeated again and again. In this loop section, we first have to charge the capacitor and measure the time. So what we do for this is charge pin is going to high, and we remember the start time in micros. Micros is a processor time variable, which is running with the processor. So we remember the start time and store it here. And then we read the analog input and wait until it reaches that 647. And when it's reached, this loop is closed. And we read the actual micros at that time, minus the start time here, means the charging time. And to get a 0 result, we have to subtract 114. It figures out that there is a time delay here of 112 to 116 microseconds. So I have to subtract here if there's no capacitance on the board to measure, then it should of course show 0. So another security check is we have a long value. It don't have to be overflowed as we get minus times, and so we check this. Else, if it's overflowing, we set it to 0. So now the simple calculation is pass time divided by resistor is microfarad. Because we use microseconds, then we get microfarad out of it. So if we calculated this value, then we can put it out on the serial port. First, output is the time. This is for checking the circuit and see if everything works fine. This is not necessary, but it's fine for controlling the circuit. So next, if microfarad is bigger than 1 and smaller than 100, we put it out with 2 digits before the decimal point and 2 digits, some digits before the decimal point and 2 digits after it. This is a serial print microfarad with 2 decimal digits. If it's bigger than 100, the decimal point and digits after it are not necessary, so I put out the integer number here. So, and if we are not above 1 microfarad, then we are below, we are in the nanofarad section. This is the nanofarad section. Of course, we have to multiply by 1000 because it's that factor in between. And if nanofarad is bigger than 10, we print out and the nanofarads and add nanofarad at the end of the line. If it's smaller than 10 nanofarad, no measurement will be output because of the error. We get 2 or 3% of error here above, but if we're going below 10 nanofarads, the error is increasing to 10% and more. So, and after we put out the value to the serial port, we have to discharge the capacitor. First, we put the charge pin to low. Discharge pin has to be an output, also put to low, so discharging starts. And we do an analog read on the measurement pin. And if the voltage on this pin is above 0, then it's not totally discharged. When it's totally discharged, then it will measure 0 volts, and it's over the discharge. And we put the discharge pin to an input, means it has a high impedance. And we wait another time until 500 milliseconds are over. So this means the output will take place 2 times a second. Every half a second there's an output. And then the loop is over and it starts again at the beginning. We charge it, put it out on the serial, discharge it, wait, and so on. Yeah. So that's it for the program. We will compile it now and see what happens with the board. It's compiling, uploading, and done. So we open the serial monitor. First of all, our line is output here, and we can see there is a 111 nanofarads output. Because I have a 100 nanofarads capacitor here in my circuit, if I put it out now, and you can see it's 0 and it says no measurement. So I got a 1 microfarad capacitor. It measures to 940 nanofarads, a little bit less. And put it out again. I've also got a 4.7 microfarad capacitor. And as you can see here, the first measurement is always incorrect. Please don't believe the first one. The other ones are fine. So 4.7 microfarads has a real life 4.6 and a little bit more microfarads. And now I use an electrolyte capacitor. You have to take care, put the minus in the minus line and the plus in the plus, of course. And this electrolyte has a printed value of 47 microfarads, and in real time it has 46, but it's nearby. So with this very simple circuit, only 2 resistors and an Arduino, you can measure the capacitance of a wide range of capacitors. Very simple and accurate. Thank you.